Okay, so we're going to talk about the central limit theorem this time. So central limit theorem is a sampling distribution of our x bar, our sample mean, will be approximately normal when the sample size is large. And by large, we mean if our sample size is greater than or equal to 30. Okay, so let's go through this problem and see if it matches all that data. Okay. So Dexter is a manager of an auto care center based on service records of 2,000 customers from the past year. The time in hours that a technician requires to complete a standard oil change and inspection follows a right skew distribution with a mean of 20 minutes and a standard deviation of 10 minutes. For a promotion, Dexter randomly selects 50 current customers and offers them a free oil change and inspection if they redeem the offer during the next month. Dexter budgets an average of 25 minutes per customer for a technician to complete the work. Will this be enough? All right, so let's think about this. First off, let's see if we can describe the shape of the sampling distribution for their X bar, for our sample mean, okay? For the samples of how many samples we want to do, 50, right, of 50 customers, okay, because we're doing 50 randomly selected customers, and we're going to justify our answer. So we want to see what the shape of the sampling distribution is going to be. So our shape can be described simply by saying we have 50 as our sample size, right, as our 50 random customers. And in this case, for the central limit theorem, our n has to be greater than or equal to 30 to be approximately normal. Well, in this case, 50 is greater than or equal to 30. So therefore, we are approximately normal. Approximately normal. Okay? And that's all you have to put when you're having to verify the shape. So we just verify the shape is approximately normal because the central limit theorem, 50 is greater than 30. So this is the key statement right there for your shape, okay? So let's talk about the mean and standard deviation of the sampling distribution of our X bar, right? Since we got 50, let's find our mean and our standard deviation for that. Well, our mean of our X bar should equal our mean of the overall work. So in which case our mean value was at 20. So 20 minutes. So our mean was 20 minutes, therefore our sample mean should be 20 minutes as well. Our standard deviation of our sample mean is going to be found out by taking our standard deviation and divided by the square root of our sample size. Well, our standard deviation for this case was 10 minutes, so we'll take 10 divided by our square root of our sample size, which was 50. And what does that give us? Let's look real quick. So we're going to take, let's see, we took 20 divided by the square root of 50, correct? No, 10, I'm sorry, 10, I'm thinking of the mean. 10 divided by square root of 50. So that should give us 1.414. So I'm going to say 1.414. 1.414. And that is our standard deviation. And also too, let's see if this is also check our 10% condition. So our 10% condition, we need to check off as well. So we'll say our 10% condition. Again, we're saying that our sample size is less than 1/10 or 10% of our overall customers in this case. Okay, So we said our sample size was 50. Sample size 50, less than 1/10 of 2,000. And I'm pretty sure we're good with that, okay? So that checks off as well. So now we've got our new mean for our sampling distribution and our standard deviation, and it checks off the 10% rule, and we know our shape is approximately normal because of our central limit theorem. Okay, so the 10% rule allows you to use these calculation figures over here. I don't want to get you confused on that. Again, the 10% rule allows you to justify using those equations, okay? So the 10% rule allows you to justify using those equations. Central limit theorem just tells you if it's approximately normal on the shape. That's the difference between those. So 10% rule verifies you can use those equations for your calculations, and the central limit theorem verifies you have an approximately normal curve. All right, so let's do something else. Let's try and calculate the probability that the average time it takes to complete the work exceeds 25 minutes. Say it exceeds 25 minutes. So let's find the probability that it exceeds 25 minutes. So again, we're going to do that just like we've been doing. We know it's approximately normal. So we can simply take this and draw out our curve. We know it's approximately normal. And our mean should be 20. And our standard deviation should be our 1.414. Oh my goodness, I could write 414. Okay. So again, our mean is 20, and we're going to say 25. I want to know what's to be for complete the work exceeds 25 minutes. So we're going to say above 25. And we just do this simply by doing our normal CDF. So normal CDF, and we're simply going to take our 25 is our lower bound, positive infinity is our upper bound, 20 is our mean, our standard deviation is 1.414. Okay, and now we can get our value of that for the area under the curve for that exceeds 25 minutes. So function or distribution, and we're going to say it's 20, comma 1.414. And we need to set up for our minimum value was 25, and we're going to positive infinity. So with this, we got a low probability, which is good, right? It's going to be pretty fast then, because in this case, we say 0.0002. So 0.0002. So we have a 0.02% probability that it'll take 25 minutes or longer. So Dexter's got a really good auto care center, right? Be able to take care of this pretty fast. Pretty fast. Now, one other thing let's look at, introduce you to, because there is a way to do this even on the Desmos calculator. So let's say we wanted to find how much average time per customer should Dexter budget if he wanted to be 95% certain that he doesn't go over budget. So with this, we're going to look at Dexter wants to be 95% certain that he doesn't go over budget. So to do this, using our data previously with everything we've got here, again, our mean or standard distribution was 20. And then our standard deviation was 1.414, okay? Sample size of 50. Now to do this, if we're 95% certain, he wants to find out. So in other words, this is the area under the curve. So what they've given you, this right here, is the area under the curve. In other words, if we were to draw this out, all right, so if we did this normal, we got 21.414. This is 20, and we're saying red, so we'll say it's way over here. So that 95% is the area under the curve. 95% is the area under the curve. And we want to know what that data value is. That's what we're trying to find out. So therefore we can see that it doesn't go over budget. To do that, we're going to use Desmos calculator for inverse norm. I'll put the link down in the description down below. And we're going to do this. So our portion on this is 95%. So we're going to go up to 95%. So we'll go up here and we'll put 95. Our mean value in this case was 20. Our standard deviation was 1.414. And then it's going to be asking whether we want it from left, from the right, from the center, or we're wanting it to the left, right? So we're wanting all the shaded area into here. And now that gives us the data value right here. Maybe kind of hard to see, but it's in the orange little value right there. Is 22.326. So we'll say 22.33. That'll be easier to do. So 22.33. So in other words, what it's telling us is 22.33. Now again, if you're using TI Inspire's inverse norm, and even if you use the Desmos, go ahead and write this out, inverse norm, in which case we're going to put 95%, so 0.95 for our probability or proportion of the curve. We're going to put our mean of 20 and our standard deviation of 1.414. And we came out with 22.33. So again, inverse norm is only used when you deal with area under the curve. They give you, they say you want to be 95% certain, 99% certain, 90% certain. They're giving you the area under the curve, and you got to find the data value it's talking about that would represent that area. So if you have a TI Inspire, you can do that there as well. You go to menu, 6 for statistics, 5 for distributions, and 3 for inverse normal. Area, you put in the decimal of it, 0.95 for the problem we were looking at. Our mean was 20, and our standard deviation is 1.414. Hit OK, and you should get 22.33, just like we got the Desmos calculator. Okay. So again, inverse norm, you put in your percentage, the mean is standard deviation. All right, guys, so this helps explain a little bit more dealing with central limit theorem and how to use the inverse norm, and I'll see you next time.